Hi, I hope everyone enjoyed lunch. I'm delighted to introduce kind of Edith Cohen, who's going to give our fourth talk of the day. And the talk's going to be on robustness to add to adaptive inputs, a case study with Count Sketch.
Thank you. So this is a joint work with a bunch of people. I'll also cover a lot of background that I think Chaim already covered and Touchable already covered in this, so it's about the robustness to adaptive inputs. Okay, so what are adaptive inputs? So basically we have any randomized algorithm. It's initialized with some internal randomness rho, and that's not visible from the outside, kind of. And in the non-adaptive setting, there is a sequence of queries and a sequence of answers. And the assumptions here is that the next queries don't depend on the prior answers, right? So this is and in the adaptive setting though, there could be a dependence. Oh, sorry, it goes by itself. I don't know why. Okay. So this arises when there is like a system with feedback, or in an adversarial setting where the goal is to construct a bad input. So that's how these kind of settings with dependence arise. So the adaptive setting is kind of more fragile to analyze. So usually with a randomized algorithm, we construct it so that for any possible input, the probability that the answer is correct is over the choices of the internal randomness is at least 1 minus delta for some very small delta, meaning for any input, almost all choices of internal randomness work. And then if we have R inputs, it's just like a union bound. So this means that if we want to find a bad input, we have to have many trials until 1 over delta kind of trials, until we find something that the randomness is bad for. In the adaptive setting, it's trickier because the output leak information on the internal randomness. And in that case, and this analysis kind of breaks down because the answers depend on the randomness, and then the next queries depend on the randomness. So we can't apply the same analysis. And as a result, potentially, by asking particular queries, we can very quickly zoom on an input that has an incorrect output. So today, I'll kind of, I'll review kind of techniques for upper bounds to make algorithms robust. And I think it's some overlap with what Chaim talked about and what Touchable also mentioned. And then I'll give some examples where if we get into the sketch with Count Sketch and kind of redesign the sketch a little bit, we can get some improvement over that. And then I'll also talk about attacks. basically a method to construct an input that is kind of adversarial for the randomness. How susceptible are the sketches that we usually know and love are to this? Is really this adaptive input, is it really an issue in practice? Okay, so I'll start with a kind of background where these techniques that we use for robustifying algorithms come from. Okay, so for the setting is like statistical queries over the samples. We have some distribution over some space, and then we take a sample, and the inputs are just like predicates, and the outputs that we want are estimates of the expectation of the predicate. And what we do usually in this setting is just look at the empirical average, the average of the predicate over our sample, and usually in the non-adaptive setting, it generalizes very well. And we can even support, if we have a sample of size D, we can expect to support kind of exponential in D number of queries and answer them all correctly. This is just a Hofding bound. The probability that the empirical average deviates by more than, with D, that is kind of 1 over alpha square log 1 over delta, the probability that we deviate by more than alpha from the empirical average deviates by more than alpha from the expectation over the distribution is at most delta. And then it's a union bound with our queries. But in this setting, it's not easy, it's not hard to even quickly come up with an example that if we can kind of issue queries adaptively, we can kind of ask which questions on like the bit representation of actually the items that are selected in the samples and kind of uncover enough on the sample and overfit the sample. And we can do it just with order D queries. So if we have the exact empirical average as a response. And then there were beautiful work by 2 groups of people. Yeah, so, and then they kind of showed, they connected this with differential privacy. And they showed that we can get better than that. So if so each time, if our predicates are not dependent on the sample, we can answer exponentially many queries. If our predicates are dependent in the sample, but we do empirical average, it's linear. But here, if the predicate depends on the sample, but kind of preserves the privacy of the sample, meaning that we can't tell if a particular element is sampled or not. It's and the privacy parameter kind of should match our accuracy, and these are just epsilon delta dp with these parameters. Then as long as the predicates that we generate kind of preserve this RDP, the empirical average will still generalize. So meaning that the predicates cannot veer, the empirical average will not be too far off from the distribution, okay? So for that to happen, of course, we cannot report the empirical average each time, yeah? So we basically, we want to, like, suppose we want kind of accuracy that is fixed, like 0.1. So we need our algorithm after our queries to be epsilon order 1 kind of DP. And then our sums, the sums have kind of sensitivity 1. And so we need to add the privacy noise with a standard deviation that is about square root of R in order using DP composition in order for the overall privacy budget to be, the overall privacy cost to be this. So basically, if this is the amount of noise that we add, we need the number of samples to be order of that times some constant, right? So that means that we can answer D-square queries using, I mean, I'm hiding here all sorts of factors, using D samples. So this is statistical queries. And then there is actually a matching lower bound. So in the case for statistical queries, this is the tight kind of. You can, there is queries that are based on fingerprinting code by Hart and Ullman and also Steinke and Ullman that improved it, that kind of reveal the sample after these square queries, okay? So now the next idea is, I think, Touchapol and Chaim also talked about it. It's by a beautiful work with Chaim, Yishai Mansour, Uri Shtemer, and now they are turning this technique to use for randomized algorithms. So here, so basically, it's kind of almost like a trick. It's basically something that is designed for samples on statistical queries. So now each instantiation, each instance of the randomized algorithm, it's treated like a sample. So these are basically the internal randomness of the non-adaptive algorithm or the sketch. And basically, we just apply the same mechanism there. So basically, we instantiate, instead of D samples, we instantiate D copies of that non-adaptive randomized algorithm. And then each time we have an input, we kind of feed it to all these copies. And then each copy gives us an answer. But we're careful with how we use the answers. We need to do some DP aggregation of these samples, and then we just output that. And then that means that we can support D-square such queries as long as we preserve the privacy. So this was very, very useful. Initially, Chaim and co-authors introduced this idea for streaming settings, but it's also useful for dynamic graph algorithms. It was also used in machine learning. And another nice thing about the use of DP here, that there is a whole machinery of differential privacy for answering a sequence of queries that kind of allows us to control the privacy loss. So we can pay the privacy cost not on all queries, just on queries that say deviate from some prior, or queries where just like the count is above something, like if it's like a statistical query type of thing, or the count is even in a narrow range. We can, like, it's a between threshold queries. So this kind of toolkit is very, very useful when designing algorithms. Because, for example, in dynamic algorithm settings or even in streaming settings, on most inputs, there would be almost no change in the output. So you don't pay for these queries. So basically, this order D-square queries that you can support is order D-square queries where kind of the outputs changed or something happens. The output was kind of far from some boundary that you incur the privacy cost. And this is kind of important because in the last year, there was a really nice paper by Guy Blanche from Stanford, where he kind of showed that you can do that without DP. you basically just produce this sample of kind of instances of the algorithm. And then for each query, you just can take a subsample and you can return anything you want. So you can even like choose like one algorithm and then apply it and return the output. And then these attacks before just won't work just because it's just the randomness of your choice. So you can still answer D-square kind of queries if you just select each randomly. And it looked, but what kind of breaks down for many of the applications is that this setup doesn't support techniques like the sparse vector that allow you kind of to pay the privacy cost, pay only for a fraction of the queries, usually a fraction of the queries where there is a change. And I don't know if it's possible to get around that. So we'll stick with this kind of framework. Okay, so now let's use this to make count sketch robust. So we can just apply this technique out of the box, but it's also, but I'll show that if we think about it a little bit more, we can redesign count sketch to kind of get a little bit more out of it. So, okay, what is a count sketch that we all know? It's basically a popular dimensionality reduction technique. The randomness row is used to, it's by, yeah, it's an old technique by Moses, who was here yesterday, not here today, and co-authors. So basically, it's like you take vectors and you produce another vector with a much smaller dimension by a matrix of the input vectors are size n, the output vectors are of size d, and basically you just take d inner products of the input vector with the other vectors, and that's your sketch. And the nice thing about the nice features of count sketch is that it allows you to recover, it preserves some good properties of the long vectors, including its L2 heavy hitters. And another really, really useful thing is that inner products of, oh, sorry, what did I do? Inner products of two vectors can be recovered from their sketches. So, okay, just a reminder, what are L2 heavy hitters? L2 heavy hitters are basically entries of the input vectors that have at least, there is like a parameter epsilon, that have at least epsilon of the L2 mass. Meaning the entry square is at least epsilon of the L2 norm square. And this is kind of a refined definition that is kind of more convenient in many settings. So basically, you only need to be to dominate kind of epsilon fraction of the tail. So you think about it is that some keys, some entries are like heavy hitters. You put them like for epsilon, like 1 over epsilon of the heaviest entries are like can be heavy hitters, and then they just need to kind of dominate the tail, which is the rest with the heavy entries removed. So this is the L2 heavy hitters. Okay, so this is what count sketch looks like. So D is the number of linear measurements, and there is a parameter that depends on your epsilon. It's about 1 over epsilon. It's kind of the width of the sketch. And basically, the format is that we have kind of the D measurements are divided to like sets of B measurement vectors each. And okay, and each set is specified by 2 random hash functions. One is H, that kind of is, it just partitions. It partitions all the entries of the big vector into B kind of buckets randomly, so that each bucket gets about 1 over B of all the entries. And then there is another hash function that kind of assigns a random sign. And this can be also presented in the form of a vector, such as the inner vector. So, okay, and then what each bucket gets is that all the entries that map to it, their sum multiplied by the random sign. Okay, so this can be presented as an inner product. So what does this give us in terms of heavy hitters? So for each key, suppose we want to know if it's a heavy hitter, we look, okay, so for each key here, we look at the bucket it maps into. The value it will contribute to it is its value multiplied by the sign. And then there would be 1 over B of the other entries. Let's say no other heavy hitters map to it. They will contribute to it with essentially a random sign. So basically, the expectation of that bucket is multiplied by the sign is basically the value of the key. And the variance basically depends on the L2 norm of the tail. So what happens is that if the key is heavy enough, this will be much larger than this. And then that the bucket will be very close to the value of the heavy hitter, if it's heavy enough. So this is, so basically you have multiple sets, a logarithmic number of sets, sorry, that are basically the value plus some noise. And basically, that's also the information that the sketch provides, no matter what estimator you apply. The original paper used the median estimator. Okay. Taking the median of this measurement. So basically, you can run over, I mean, there are much more efficient ways to do it, but you can run over all the keys and then look at all the buckets in each set, look at the buckets that this key falls into, and then multiply that value by the sign. That's how you do the recovery. And then you get a number of, from each set, you get one estimate for the value of each key. You take the median. Okay, so this is how it works. Okay, so now we want to apply it. To apply this robustness wrapper with a count sketch. So the usual way is the straightforward way. We basically we take this whole sketch, like logarithmic number of sets of measurements, and we basically replicate it multiple times, and then we ask how many queries we can answer. So basically, for each query, which is an input vector, we need to run over all the keys. But because of these sparse vector-like techniques, we only pay privacy costs for the keys that are actually heavy hitters, which there can be at most B is like that number of buckets, 1 over epsilon of them. So basically, it's like for R inputs, we basically need to issue R times B queries to the sketch. So we lose a little bit here. So basically, we need the square root of that with the robustness wrapper IID sketches of that size. And then if we plug it all in, with a sketch of size D, we can answer D square epsilon cubed we can process that many different inputs. So that cube kind of seems out of place. We wanted to get rid of it. Okay, so one improvement, one is basically to just reduce the privacy units instead of charge the whole sketch, log sets, logarithmic number of sets of for every input. We just reduce it, but that doesn't give us that much. It doesn't improve this factor. The idea that we used in the end is to reduce the privacy unit just to like a single bucket in the sketch, because every input kind of we answer many queries for many keys. So the way the privacy analysis goes, we kind of charge for each such query on every single key. We kind of charge the full sketch, the full set for every query, and then we can get less out of it in terms of the privacy accounting. So the idea is to kind of just like charge like a single bucket. But the issue is that we can't fit it into that same framework, because these buckets are not independent, they are dependent. They are based, the buckets in each set based on random partition of all the keys. And the buckets in a random partition kind of are not independent. They are not, the randomness is not drawn independently from the same distribution. So we kind of needed to redesign the sketch. But if we, I mean, we can see, but that allows us to kind of reduce that cube to a square, which is kind of the optimal. So we needed to do several redesigns. So we also kind of, we needed to kind of tweak the privacy analysis so that so each bucket is only carefully charged to the queries of keys that kind of map to that bucket. So, and then we kind of needed a different estimator we used that kind of has the predicate form. So to identify the heavy hitters rather than medians, we kind of looked at the number of buckets that that their sign aligned with the sign of the random keys. So basically now that modified count sketch kind of looked like that. So basically, instead of the hash function that kind of partitions to B buckets, basically every linear measurement is basically every key maps in with probability that is 1 over B. And then it's 1 or minus 1 with equal probabilities in this case. So this is kind of a slightly modified count sketch. It's basically the same distribution at each count sketch bucket. And it's the performance of estimators is very much the same. And we can also do a kind of analysis with limited independence. But maybe it loses just a little bit because it's not a perfect partition. Because then instead of getting one estimate from each set, we just get kind of a random number kind of estimates for each key. So now we did all that work kind of just to be able to apply that framework that kind of works with IID samples. And I don't know if this redesign was necessary. It kind of really feels that count sketch as is, with the buckets, we should be able to somehow get the same, do the same with. But I still don't know how. I mean, it's basically that hammer, that differential privacy hammer kind of is designed for IID pieces of randomness that are kind of IID. So, okay. So now I want to talk about the other end of things, which is attacks. So with statistical queries over sample, these were like tight. In a non-adaptive case, we could answer exponentially many queries in the sample size So with the exact estimator, we could answer only D queries, and that was tight. And with DP, we could, instead of D, could get D square, and that was tight. But with randomized algorithms, with the wrapper, we get this kind of upper bounds, but we don't have we don't have lower bounds. And we can look at any particular sketching structure or algorithm, and then maybe the estimator that it comes with is already robust, right? Maybe it's much better than this, and maybe this D square is also we can get. I mean, even if that doesn't work, maybe we can get better than this D square. And our initial feelings when we worked on that was with Tamash, Jelani, and Uri, and two students, Moshe and Shin. Our initial feeling was that we should be able to do something better with count sketch. But it's apparently not. Okay, so now generally for attacking linear sketches, the attack goal is to produce an input with a sketch that is kind of out of distribution. And then we look at the number of queries we need to issue and the number of rounds of adaptivity. So this is just, okay, so the attacks, okay, so, okay, so this is, so now we're looking at not just count sketch and heavy hitters, any form of dimensionality reduction via linear map, and the count sketch, the AMS sketch, JL transform are kind of examples to that. Also kind of compression layers in trend layers in neural networks are kind of example of that. And then basically the goal is of the attack is kind of to construct bad inputs. And in the literature, there are kind of two types of attacks on such linear sketches. Or linear maps, let's say. The first is kind of, so basically you have kind of inputs of size n, and there is some linear map, and you get something of size d. And you want to, okay, so one thing you can do to attack is basically to add a lot of noise to your vector such that it's no longer recognizable, but you can still recover it. So this is, so basically, the noise that you add can have a huge norm, but then it kind of falls in the null space. So theory work on that was on linear sketches was by Hart and Woodruff in 2013, and then there was this work in 2020 that they actually tried it on MNIST. And basically you take these numbers and you add a huge amount of random noise, a huge norm, and then the kind of neural network can still recovers the number. So we can see the number, but the number is, we can see it now, but kind of the noise is invisible to the sketch. The other type is basically add a tiny little amount of noise to the input vector, but that will completely get the sketch out of distribution. So there had been some work on that for the AMS sketches and also for constructing adversarial inputs for neural networks. So basically, we just want to quickly, in these attacks, the goal is to quickly zoom in on a small noise that kind of completely throws away the sketch. And the question is how hard it is to do. And it seems like, I mean, we explore this with all sorts of linear sketches, but it seems like that this square is kind of inherent. Okay.
Sorry, quick question. On the first one in the, on the first attack on the previous page, what is the downside of this? It sounds like a noise, which is the best possible thing you could hope for. It's in the null space of your sketch. It's not actually altering anything. How is this? What's the attack?
So the attack, okay, so I called it an attack, but basically it's just a kind of a way to mess it up. It's like you can't see the input, but then yeah, so I don't know. You can think of it as an attack. It's kind of
it's an attack in the sense that if you were to observe the adversarial input,
yeah, so
you can't answer it, but the algorithm can still answer it anyways? Or?
Yeah, so like you don't know what it, yeah, like something like that. It basically confuses the sketch, right? Like you can't, the human, this time, the human can't tell, and it doesn't confuse the sketch, sorry, it confuses the human. The human can't tell what it is, but the sketch still recovers it. So, I mean, yeah. And here, it's like you just add a little bit of noise that the second thing that actually confuses the sketch. So it's kind of two types of ways to mess up with these linear sketches. Maybe I shouldn't have used attack, right? But
gotcha. Thanks.
Yeah. Okay. Okay. So now. Okay. I don't know. Okay. So, okay, so for count sketch, so our first question was whether the classic estimator was kind of already robust. So I'll just review that. So we basically constructed an attack that is kind of linear in the size of the sketch, which nearly matches the kind of trivial upper bound of using a fresh part of the sketch, a fresh subset of rows for each query. That was against our initial intuition. We thought that because of median and this and that, it will be a little bit more robust. And interestingly, the attack had a very small constant, and it actually was barely adaptive. You just, all the queries that you issued were kind of together, and the only adversarial input in the end, that was the only one that depended on all the queries. And it was also fairly efficient. So basically, count sketch, so basically you kind of look at the noise added to each bucket. So basically, this is not the number of queries we needed in order to kind of to create a new vector for which the noise part, the bias of the buckets is kind of exceeds by a factor of R the bias that we would expect. So, I mean, the noise that we would expect, meaning it can obscure heavy hitters that are a factor of R larger, because the noise would be kind of factor of R larger. So this is like, and it's a pretty natural attack. It's just basically you take a vector with some heavy hitters and you just add random noise in different places, and you just combine this. I mean, okay, I'll talk about the general attack. And okay. So now the question is, can we do better than this quadratic robust estimator? And then we could show the following, that basically any correct heavy hitter estimator for count sketch can be attacked with quadratic number of inputs. So the median, the simple median estimator can be attacked with the number of inputs that is linear in the size of the sketch, but any correct estimator can be attacked with number of queries that is quadratic in the number of the sketch. And it's still like this weakest adaptive setting that basically the queries are completely independent and issued together, and the only thing in the end is the adversarial input. And also the attacked vectors are very natural. It's like, again, one heavy hitter, and the rest are and random noise. And it also can be implemented in a streaming setting. Okay, so I think I don't have actually much time to cover that. So what does the correct heavy hitter estimator? We made it as weakest as possible for the sake of the attack, and we could still attack it. So basically the requirement is that every key that has a 0 value cannot be returned. So basically the estimator returns as a subset of the keys. And if the value squared is more than epsilon fraction of the L2 norms, it must be returned. And the rest we don't care, and we still call it correct. And any estimator that kind of takes a count sketch and returns returns something like that. And it can be a different estimator each time, but we can still attack it with meaning we can produce a bad input after a number of queries that is quadratic in the sketch size. And basically, this query vector, attack vectors have a very simple form. It's basically all have the same heavy hitter key, and then say these joint subsets that are basically just random tails, we call it. And the algorithm is basically the only thing you could use with these estimators is basically you issue queries with different random tails and kind of the same heavy key, but you draw kind of the weight of the key from some distribution. And then if the algorithm tells you it's heavy, you add this noise vector positively. And then if it tells you it's not heavy, you subtract it. And then after a quadratic number of queries, you get, I think I'm almost out of time. You combine all these tails with these signs, and then and the idea is that the bias adds up. So a key that is reported heavy is slightly more likely to be biased in a certain way. Like, sorry, a tail that is reported heavy is slightly more likely to be biased in a certain way. Okay, yeah, there's no time. Okay. So, okay, so this is a very general form of attack. It also works for the AMS sketch. Also shows that after a quadratic number of queries, you can fail it, no matter what estimator you use. Any estimator that under some value returns 0, over some value returns 1. You can kind of use the same kind of attack technique and find a bad input. So just for fun, we tried this attack on CFAR. It's like a ML dataset of images. So basically, we just added non-adaptively random noise. And then based on this time, we kind of looked at the softmax results. And if the softmax was higher, we added it positively. If it was lower, the softmax prediction for another class, we added it negatively. And basically, it was pretty effective in reducing the performance with relatively small number of queries. So basically, the main question here is like maybe a kind of generalize this kind of a simple ideas so that it's like it works for count sketch, it works for AMS, it works empirically for just neural networks that are not even completely linear in the end, but there are linear layers. Kind of show generally what's going on. Understand this better. So these attacks, again, the vectors are simple, natural, almost not adaptive, and they kind of meet this upper bound. So, and they can be applied to any, the attack format can be applied generally. So how far can we push it? Okay, thank you.
Any more questions for Edith?
I have a question. Sort of towards the beginning, you were talking about how we care about adaptivity, not just because there's an adversary, but also because we might be in a system with feedback.
Yes.
Are there some examples where you can design a system with feedback where these sketches break rather than an explicit attack?
So you can think about natural algorithms that kind of use the output of the following of the prior things. I don't have a good example in this case, but kind of the attacks that we do use, which is just like there is a signal and then we add noise, but the noise could be also kind of maybe a natural noise, so you kind of observe from the outside the outputs. And because the attacks that we kind of used are essentially non-adaptive, it's like you have a picture like a dog, and then you try it in all sorts of noises. So we added actually random noise, but maybe even noise that is not completely random. But you just like look at the biases. You just like look at the responses. So that maybe even that alone can kind of allow you to construct a bad input. I don't know, but it doesn't show up in the algorithm itself, in an algorithm in some way. But at least you can get this information just by observing a working system. Enough information to kind of find something that fails it, right?
Right. Thanks.
Thank you. Could you hope to have attacks that are, say, insertion only or deletion only and still work? Like, say, you're only allowed to add things in some, if that question makes sense.
You mean in a streaming?
Yeah.
Okay, so we kind of, you mean just the positive updates?
Yeah.
Yes, so the noise that we added is signed. And that was kind of critical.
Yep.
So, and also with positive updates, things don't change that much.
Yep.
So you don't, like if you look at like norms or heavy hitters, it's like, it's logarithmic maybe number of changes, so it's not as much of an issue, right? So,
yeah. So maybe this is easier against such an adversary?
Yeah, it's like David, I think, can answer this better.
Okay.
But he's doing soda, I don't know what he's doing. So positive updates and streaming, basically, it's like you get very few changes in the output.
Yeah.
So maybe,
Thank you.
So there's this gap between this like exponential number of queries you can do in the non-adaptive case and this like d squared you can do in the adaptive case, right? Is there any hope for like a sufficiently weak adversary where you can hope to find some middle ground? Or is this sort of like a completely hopeless ideal in some sense?
So it's like very problem specific, right?
Okay.
I mean, some people looked at all sorts of weakening techniques for adversaries, right? Mm-hmm. But the frustrating thing is that even for for count sketch, for AMS sketch, it's like okay. it's this square and with the regular, so our intuition was that no, that this cannot be real, but apparently it is.
Fair enough.
Yeah.
Cool, thanks.
Any last questions? Okay, well, let's thank Edith once again.
Thank you.
And so we'll meet back here